correlators. Okay. Or you can do this for, I guess, the Robinson bound. So there are many, many ways you can quantify scrambling at early times. Well, but however, no matter which quantity you choose, if you wait for a bit longer, all these quantities are going to settle down. This is usually what we mean by equilibration. Okay. Nevertheless, this is not quite the end of the story, because right now these two notions are arguably closed system notions of thermalization. Okay, so indeed, right now I haven't mentioned much about the bath. Okay, okay, so these are closed systems. So for today, we'll not talk about closed system. We'll instead focus on an even later time regime where the bath becomes important. Okay. So in this very late regime, that's our main focus. We're going to ask, does our system actually get entangled with the bath? More precisely, we ask, does our system in trace distance become very close to the Gibbs state? Okay. Okay, so to reiterate, we be focusing on the open system setting, and it's kind of what allows us to write down these very precise notions of thermalization. Okay. All right, so that's our main focus today. And of course, this question has been, people have been thinking about this for a very long time. The notion of Gibbs state was introduced since classical statistical mechanics. In a quantum case, people do also think about a Gibbs state, but often it's very difficult to justify it, simply because there's so many different possible systems to think about. Okay. Nevertheless, physicists are extremely creative. People cook up all these different notions that relates and perhaps even generalize thermalization. So this is by no means an exhausted list. Okay. So these ideas, they're kind of vague, but you kind of know what's happening. But it's very hard to make concrete connection between them because definitions are often incomplete. Nevertheless, you can play around with these ideas in concrete toy models. This is what people do quite often. You can take some large n limits, you can do some numerics, and you can indeed observe some of these phenomena. Okay. Today, we're going to take a slightly different approach. We're going to take more of a mathematical physics approach. We're going to try to draw a concrete connection between these ideas. Okay. So we're going to pin down write down a very specific definition of ETH involving random matrix theory. And we're going to tell you how it relates to thermalization in the sense of open system thermalization to Gibbs states. Okay. So this is where our work sits in the literature of quantum chaos. I also know there are quantum information audiences. So let me briefly mention the motivation from there. So let's suppose you have a quantum computer. Then one thing you can do is to simulate materials. Okay, so simulate your favorite quantum system. Okay. So there, a key subroutine is to prepare the thermal state or ground state. Indeed, to do any experiment, you better start with a reasonable state. Okay. And a very valid choice are these ground state or thermal states. However, once you write down these definitions very carefully, you run into weird obstacles. So complected theory would tell you that these problems could become extremely difficult, that is QMA hard, in the worst case. So this is some version of quantum MP problems. It means that we don't even expect quantum computer to solve these problems efficiently. So this feels pretty counterintuitive, because based on our physical intuition, it seems that many things thermalize. Okay? At least that's what our daily experiences in lab tells us. This is what thermodynamics tells us. So you see, now there's this kind of weird dichotomy between two different fields. And this mainly tells you that they're just different kinds of Hamiltonians, and the answer really depends on which kind of Hamiltonian you cares about. And today, the purpose of this work is to borrow from these physical ideas and argue that these quantum algorithms could work efficiently in preparing the thermal state. So any questions so far? So if not, let's move on to the technical backgrounds. So let's begin with the classical case. So let's take classical Ising model. So each of these guys could be plus or minus ones. Okay. So presumably there's some local Hamiltonian that governs the interactions. And the task is to produce its thermal states. Okay. So often this is called Gibbs sampling, I think in the CS literature. So this task has been very thoroughly studied, both theoretically and numerically. So what people do, it's already a very old idea, is to do metropolis sampling. This is one of the techniques in Markov chain Monte Carlo methods. So what it does is to randomly flip these bins. And then you're going to accept or reject according to some probability. Okay? And this depends on the temperature as well as the energy difference. Roughly, you can think of this as the computer trying to emulate the behavior of a bath. Okay? So even though there's not really a bath here, it kind of by hand put in the Boltzmann factor. So formally, this really nicely is a Markov chain. You can open your Markov chain textbook and think about how to analyze these subjects. There has been a lot of literature studying all the mixing properties of these Markov chains. And let's look at this figure more carefully. So each of these nus are the energy labels of the configurations, and each of these one could host many different possible configurations. And whenever you're doing a sampling, you're really traversing all these possible configurations, and you hope this process mix very quickly to the stationary distribution, which is the Gibbs state. Okay. So this is a classical picture, and for the quantum case is very similar. You can also think of like an algorithmic approach, or like an actual analog approach that you keep a physical bath. So both are possible. They're both people study both of these ideas. For today, we're going to focus on the right-hand side. This one is more physical. And in our paper, we also study this metropolis sampling. However, we recently realized this quantum version of metropolis sampling. There seems to be some concerning issues with phase estimation that we're still investigating. We plan to update our paper soon, so we're not going to talk about this part. Okay? We're just going to focus on the right-hand side. Okay? All right, so let's consider the open system setting. Very carefully, we have our system interacting with the bath. Okay. So here's your system Hamiltonian, here's your bath Hamiltonian, and there's some interaction terms connecting these two systems. Ideally, this coupling should be pretty weak. That's why you can make the distinction between a system and a bath. Okay. This is often called a weak coupling regime. And well, now you look at this and you say, well, there's a lot of parameters. Nevertheless, Davis, a long time ago, tells you that this open system setting can be effectively captured by Markovian description, and this is the Lindbladian that governs this dynamics. So there are lots of notations. Let's unpack them. So these rows are the states for your system. Okay. And this operator A's, they're coming from this interaction terms. Intuitively, this is kind of that your bath is probing your system by flipping your spins. And you can really think of it as a classical random walk on an energy basis. These interaction terms are driving the transitions between different energies. Okay. So now you say, well, so what does the bath do, right? It doesn't. This expression doesn't seem to depend on temperature. Actually, it does. It depends on the bath and the temperature implicitly by this function gamma of omega. So this is some weight that you multiply with all these transitions. So roughly speaking, what it does is to suppress the heating process and kind of boost the cooling process. Technically, there are some detailed balance conditions here. And then the rate of these two processes are related by a Boltzmann factor. Okay. Technically, this is also related to the KMS condition. So anyway, all these weights tells you that a fixed point will be a Gibbs state. Okay. So right now, you may think that, well, this picture looks terribly familiar. It looks very much like the classical case. So indeed, this is a classical walk. And in principle, if you know all these transition rates, you can estimate its gap. And that means that you can know how fast this process converges to the Gibbs state. Well, there's one very big caveat. There's actually something wrong here. That is, in the derivation, Davis took a weak coupling limit. In this limit, you effectively allow yourself to evolve the system for an infinite time. Okay. So what's happening here? So if you look at this classical process, it effectively distinguishes even the nearest energies. But in any realistic system, if it's kind of large, the level spacing is going to be really, really small. It's going to be exponentially small in the system size. Well, then based on the energy time uncertainty principle, it means that you need a very long time to distinguish these different energies. Therefore, this description only really works if your system is pretty small. Say you have 1 or 2 qubit. So in practice, people don't use Davis generator for large systems. You have to do other things. So any questions right now?
So could you, sorry, please.
Oh, no, go fast.
Okay, so could you give the relation between that capital, there's a 2 capital A, right, in this slide. So one is without omega and one is with omega.
Oh, yeah.
Sorry. Could you explain the difference of this operator?
Right. Yeah, sorry, I didn't write down the definition. So, so these A of omegas, they are the Fourier transform of these operator A's. So it's so you can think of it as you're diagonalizing the Hamiltonian, okay? And then you write
just a moment. So which whole Hamiltonian or the joint Hamiltonian or the
system Hamiltonian?
System Hamiltonian. Okay. Yeah.
Sorry. Yeah. To reiterate, these omegas are labels for the energy difference of the system Hamiltonian.
Yeah.
This omega is kind of like the energy differences.
Yeah. And how this capital A is related to the capital A appeared in the right-hand side. That's in the summation.
That's
Yeah,
right.
yeah.
That's right.
Yeah,
That's
yeah,
right. That's right. So it's like the matrix element between energy states.
Uh-huh.
Yeah.
Ah, okay. Yeah. Yeah, thank you. Yeah. Difference between
Hi, Anthony.
Hi.
This is Kotaro. So,
Hi.
is the problem caveat here also appears in classical case?
Yeah, that's a very good question. So I think the classical case people didn't start with such a low-level model. At least I don't know. Like I think people study. I think when people study this classical thermalization, I think people just start with the process. I think people didn't try to start with this system-bath interaction.
Oh, I see.
Yeah. And if you want to be very careful, I think, well, in a classical case, usually you expect this level spacing to be bigger, because if it's like, I say, all polys, then it might just take like discrete energy values. So if there's some characteristic energy scales, then you kind of only need the process to be longer than that time scale. So it may not be this level spacing. In other words, level spacing might be kind of big in classical models.
Thank you.
Yeah. So yeah. So that's very important questions. It will actually show up in the next slide. Okay. All right. So there's this issue with this energy time uncertainty principle. So now, if you want to confront this question, you have to accept that you just can't resolve this tiny level spacing. Okay. So you have to come up with something else. Okay. Okay, so here's an attempt. So let's consider a very naive toy model. Let's just start with a Hamiltonian and then let's round it. Okay, so that means that we artificially make the Hamiltonian like a histogram. Okay, so all these energies are going to be the same. Okay, so there's going to be these discrete energy values. And we're just going to make them have the same energy, so it has a huge degeneracy. Okay, so this toy model is intended to make this coherence at nearby energies pronounced. Okay. So for example, if you, as Kotaro mentioned, if this Hamiltonian is classical, if it already starts with this kind of discrete spectrum, well, then that's fine. Okay, it's already in this form. Okay? But in general, if it's not, then let's consider this following toy model. Okay, that is unphysical, but it captures a lot of physics. Okay. Okay, so this is the perhaps strongest assumption, or at least for this toy model. You don't necessarily need this assumption, but things get very complicated. We do work out these things in our paper, but it gets messy. I think this rounded Hamiltonian, which we'll stick to throughout the talk, is largely sufficient. Okay, so before I present some rigorous results, let me just add a lot of technical assumptions. Just to be consistent. So we impose Markovianity by refreshing the bath. So you can impose Markovianity in many other ways. I think people have their favorite ways of doing it. This is just one of the ways. We also allow ourselves any polynomial runtime. Okay. So the point here is that we don't want it to be exponential. We want it to be polynomial, but we are kind of okay with big polynomials. And we also allow ourselves to pick up our favorite fermionic bath of reasonable size. So again, these assumptions can likely change them a little bit. This is just to be concrete. Any questions so far?
Is this a polynomial runtime means just small l or just t? And in that, if the polynomial runtime is with respect,
everything. So there are many resource calls. So there's this L, like how many times you need to restart your bath, and how much. So there's this accumulated time. So okay, so some things multiply together, but now we just say, okay, let's just throw in some big polynomial. We don't care.
Okay.
Yeah.
Ah.
So yeah.
Sorry, I have a question.
Yes.
Why do you choose a fermionic path? Like, because you can map it to qubits ultimately, or like?
I think this is just, it's not very important.
No.
It's just that I think people in the old literature, people do this, so just
Oh.
do it. I think you can definitely do other things. And
Okay.
indeed, fermionic path, it's free, so it's essentially just some.
So bosonic path can
it
also
can be
be
very simple.
implemented.
Yeah, I think, yeah. So all these argument doesn't quite matter. This is just one
Oh.
particular choice. It's not,
Okay.
not too deep. Yeah.
And another question: can you extend your theory to non-Markovian systems? Like, I don't know, introduce a memory
so
kernel or?
right now, no. Right now, all of this is based on the semi-group methods. Like you have some map and you apply many times. So
Okay.
if it's not Markovian, we have to change tools.
Oh, okay.
Yeah.
Thank you.
Yeah. Because right now it's kind of like we're implementing some Markov chain, and
Okay.
that's Markov.
Ah,
Yeah.
Okay. Sure.
Yeah.
Thank you.
Yeah. Thanks. Nice questions. All right. So with all these assumptions, then you can now write down something concrete that is different from the deduced generator. So here's the form. It looks very complicated, but what it's doing is just a semi-classical random walk. Okay, so what's semi-classical about it? So you see that when you apply a flip, these operators A is going to drive transitions. Then it's going to have some of these global mixing parts. It's going to change the energy labels. Okay, so it's going to go between different subspaces. However, there's also quantum part of this process. And that's precisely when some rotations appear in each of these subspaces. Right, because now you have a big subspace, there are a lot of degeneracies, and your operator A could just change the state without changing the energy. Okay? And this part is quantum. Right now, it's not obvious what kind of mixing is happening here. Okay, so this is what we mean by semi-classical. Okay? So you have some kind of coherences at nearby energies, but if you're at different sites, different discrete labels, then they're kind of incoherent. So I find this picture very, very nice. This is how I think about all these processes. But of course, this is a simplifying picture. If you want to have like a real generator that considers the unrounded Hamiltonian, to be fully rigorous, this gets very messy. And perhaps there could be some simplification, but right now we have some very messy object. Yeah. Okay. All right, so this is the picture. Today we're going to stick to this guy. And the main guiding question, now that I have presented the generator, is how does this semi-classical random walk mix? Because right now it's not very obvious. This global part is kind of classical, so it's okay. But this local part, how do you get rid of all these coherences? Because there could be like exponentially many states inside each of these bins, right? Yeah, so that's the main interesting question that we will answer today. Okay, so if you ask this question about fast thermalization, there are a lot of mathematical physics literature studying these. So let's start with the classical literature. People have been working with spin glasses. I don't know too much about it, but I know there are a lot of literature there, and there's still recent progresses. For a case, in terms of fast thermalization, or people call like rapid mixing, there's a lot of these very nice results about this Ising model on lattices. Okay? So there people have a very complete picture that thermalization is related to the decay of correlation. Okay? So there's this if and only if conditions. That's very nice, very well understood. However, in a quantum case, things become much more mysterious. right now, this classical approach only generalized to commuting Hamiltonians. It's already pretty hardcore. There are a lot of analysis going on. It's also very recent. And more generally, general Hamiltonians are probably going to be non-commutative, right? That's what happens. And right now, we don't know any convergence result, okay? Or to be very precise, any fast convergence result. So if you give yourself exponential time, you can do everything. But if you only want like a polynomial scaling thermalization time, we don't know. And this is precisely the scope our work attempts to address. We show that chaotic systems thermalize quickly in polynomial time, but with strong assumptions. Okay, so we're going to borrow from this assumption called ETH. So again, we are not proving the entire theory. This is still very open. We're only trying to understand it better by introducing these ideas from physics. Okay. So any questions?
This is just a comment, but so there's a paper by Tomotaka and I and Fernando about some, condition decay condition mutual information on high temperature Gibbs states. And apparently, you can show the gap of the William in Castellano's paper in non-commuting case if the temperature is sufficiently high. So I think in that case also, we doesn't publish it, but you can ask Fernando if you are interested.
Oh, interesting. Yeah. Sorry, I didn't know that, but yeah. Okay. Cool. That's very interesting. Yeah. Okay. Yeah. So I think that for high temperature, I think there's some possible approaches. But I think when the temperatures kind of get slightly lower, it becomes kind of very much unknown. Yeah. Thanks, Kotaro. Thanks for adding that. Very nice comment. Cool. Okay, so now let's mention our main assumption, the eigenstate thermalization hypothesis. So you might feel this is kind of tautological because this hypothesis itself has thermalization in it. It's not tautological, it's more of a terminology issue. So let me clarify. So this is ETH. The eigenstate thermalization hypothesis states that or it considers a Hamiltonian and an operator. And we say this pair satisfy ETH if this operator looks like the following in an energy basis. So these guys are energy eigenstates of this Hamiltonian. Okay. So ETH tells you that this operator changes very slowly in this diagonal part. Okay, so it's just like a very tiny part of the matrix. There's a diagonal. Okay. So this turns out to give you static thermodynamics for closed systems. Okay. So in fact, from this you can derive that eigenstates give thermal expectations. Okay. And this in fact goes into the name of the hypothesis. I think this goes back to Schenicke. Okay. However, you realize that this doesn't tell you an awful lot about the dynamics, because it doesn't tell you anything about the things outside of the diagonal. And indeed, if your state is entangled, it doesn't quite tell you what happens, because it misses all these coherence or like these off-diagonal parts. Okay. So in order to get dynamics or any kind of equilibration out of ETH in this way, you require some infinite time. Okay, in other words, you need to wait for all these off-diagonal parts to dephase. So here you also need to wait longer than the inverse level spacing. So this part of ETH, I think, is what people commonly think about when they think of ETH. However, this doesn't tell you much about dynamics, any kind of finite time physics, unfortunately. So for today, we instead are going to need a different part of ETH. It's the off-diagonal prescription of ETH. So ETH tells you that the off-diagonal part obeys random matrix theory. Okay, but you have to be very close to the diagonals. So essentially, you can thicken the diagonal part, and all these parts all behave like random matrices. So a priori, it's not very clear where all this randomness is coming from, because you start with some really simple Hamiltonian, you have some very simple operator, but all of a sudden people tell you that, hey, you get random matrix behavior. Okay? But this is very mysterious. It's very hard to prove. But you can do numerics, and it seems to come up. Okay, so there are some empirical evidences of the size of this band. There's some scaling, and for us, this polynomial is good enough. Okay, so n is the system size. Okay, so we're just going to assume this. Okay. And perhaps what's more important for our proof is that we're going to need ETH for many operators. Okay, so usually people think about ETH for one operator, but now we kind of need how they relate to each other. We're going to assume that different operators can be modeled by independent Gaussian matrices. So this independent is very important. This is also quite unconventional, but this is what leads to our proof. Okay. So any questions about ETH? If not, let me now present our main result using input from ETH. Here it is. We show that if you assume ETH in the sense I told you, then the following generator, so this guy, the semi-classical random walk, converge quickly. Okay, it means that for whatever input state you have, it's going to quickly thermalize. It's going to converge in trace distance to the global Gibbs state, okay, which is very mixed. Okay. So there are some requirements on the runtime. So it has to be kind of long, but it depends only polynomially on all these parameters. Okay. And in particular, all of these only scales polynomially with the system size. So no exponentials here. Okay. There are a lot of parameters here. Let's highlight some of the interesting ones. It depends polynomially on the temperature. So it means that this process works pretty well even you go to low temperature. There's nothing crazy happen. Of course, you could have a phase transition where your system becomes not chaotic. ETH could fail, and then we don't know anything about those regimes. Okay, it could become a glassy phase, then yeah, it shouldn't thermalize. Okay. It also depends on the random matrix scale. This guy. This is maybe a proof artifact. It's because we're only using the transitions in this tiny band. Okay, but fortunately, this band seems big enough, so it's polynomial. Okay, so last and the most important one is that this convergence rate depends on the gap of a classical random walk. So this is very mysterious. So right now it should be very confusing why there should be a classical random walk coming up. Okay. And now I haven't told you what this is. Okay. But it will become clear in our next few slides. Okay. So this is the main result we have. So any questions?
Lambda related to the lambda which appeared in the much before, or this is just you will define what you define here, or lambda.
Sorry, can you repeat that? I didn't. I didn't.
Sorry, so I want to ask about this lambda R.
Oh yeah. So I will
This is-
define it.
Okay.
Yeah.
Okay.
That's the
okay.
only. Yeah, that's the part that I haven't tell you yet.
Okay. Thanks.
Yeah. Thanks.
So can I ask a question?
Yeah.
So you now consider the ETH for the system Hamiltonian,
Right.
but we can also consider the ETH for the total Hamiltonian, which is a closed system. And can we find the same summarization behavior or time scale from the total Hamiltonian ETH?
Yeah, that's a very interesting question. That's maybe more of a follow-up. So right now, it depends on what you mean. So yeah, you need to set out the problem a little bit differently. Because right now, if you say I have ETH for this 10 different operators,
I see.
okay, for this for a system of interest, but maybe now you choose a new operator and it doesn't need to hold. So here, I think here is slightly different. Here the statement is that you only need some set of operators that satisfy ETH, and whenever that works, you get a Gibbs state, and you get a true Gibbs state, and it works for all other operators. So if you instead consider that, oh, my total Hamiltonians, my total system, system plus path, satisfy ETH, then yeah, we need to sharpen the question a bit more. But that's a very valid future direction. Yeah. You might also need to change, like tweak the ETH in some way.
I see. Thank you.
But thanks. That's definitely very natural, a very nice question. Yeah.
I need to make sure that this detail of this dynamical equation, Lindemann equation. So you said that okay, you assume the interaction like random walk in the energy basis. So this is this encoded in this the function gamma omega tilde?
Right. So it will become clear. Yes, exactly. Yeah. So this lambda hides a lot of things.
Okay, and
yeah. Thanks.
And you also assume that this matrix element of this this board A obeys this ETH. The matrix element of this board A in the right.
Yeah, that's right. Yes.
Okay.
Oh, maybe I didn't mention that. Yeah. So sorry. So yes, we need ETH for these guys. Yeah.
So is it okay? So maybe it's okay, but is it reasonable that this only the simple operator appears in the dynamic equation motion? I mean, do we need a heavy non-simple operator can appear in the? Are they negligible somehow?
So yeah. So the question is, well, what do you pick for these guys? Like, what do you choose?
Right.
So ideally, you should just be like, say, single side polys or like two body polys. So right now you see that how many terms you need. You actually only need like constant many terms. So then somehow, like, even if you only have few terms that's interacting on your system, you can think of it as being like this dynamics of the Hamiltonian itself is kind of scrambling everything together. So even though, say, you only have two like interaction terms, then somehow this is enough. Okay, you need constantly many, but like, yeah, you only need some collection of them to work.
Okay.
You don't need to take like, I don't know, like 10 body interactions. No, that's not necessary.
Okay, I see. Thanks.
Yeah.
I'm curious about how big this polynomial is in terms of n. So is this close to like linear or like a bigger number, like 100 or something, or you have no idea?
So pessimistically, it's like n to the 10 or 40.
40. Oh, okay.
No, it's a lot of this is coming from these parameters because we don't know how big these guys are. So for example, this guy could be like n cubed.
Yeah.
And once you multiply a few more times, you get like 40.
Okay.
But however, like in a very optimistic regime, so if you kind of okay with hand waving a little bit, you can expect like almost like linear, like very fast mixing.
Okay.
Yeah, so you can get very small polynomial if you
Yeah,
But
I'm just curious.
typically
For
you might
example, if you add a little bit more assumptions, like the Heisenberg type Hamiltonian or something, can you easily reduce the polynomial? But of course, it's a little bit tricky because you have to combine this Heisenberg or concrete type of interaction with ETH assumption. But you know, if you can deal with these, is there room for improving this polynomial?
I think right now the biggest place where this blows up the polynomial is this ETH assumption.
Okay.
So yeah.
I
I think
see,
yeah, that's the main thing. I mean, otherwise, like I think there's some semi-group inequalities, or like when you change norms, sometimes you get an additional factor of n, like log dimension. That's pretty common, and maybe those can be removed. But right now, what's blowing up the polynomial is just these parameters that we don't quite know.
Okay, yeah, thanks.
Yeah, thanks a lot. Thanks a lot. Okay, so maybe I should move on now. Oh, sorry. So let me also mention, I have dropped a lot of assumption about density of states. So right now, I kind of roughly assume that this density of state is pretty smooth. It's like a Gaussian. We just want to avoid that when this density of state kind of oscillate crazily. So that might change things, but I think usually this is kind of fine. Okay. And this is for the rounded Hamiltonian. If it's unrounded, some of these parameters get bigger, even bigger. I think this interaction terms need to be more. But qualitatively, it's the same, very much the same physics. Okay. All right, so let's talk about a proof idea. So how does it work, right? So now you have this semi-classical random walk. You have this global part that you understand very well. It's like classical, like moving things around. But now you have this local part that's quantum, and why does it mix, right? Okay. And how can you even come up with the time scale that this happens? So let me start with a related idea. So it's expanders. So let's start with the classical expander. So now you have a bunch of vertices. Okay, so it's some you can think of it as a graph. And then now you randomly connect these graphs, these vertices. And well, if you do them randomly, then you expect this graph to kind of be expanding. So if you take some small set, you expect there to be many outgoing edges. Okay, this is rough, roughly what it's doing. And more concretely, you can take this to be coming from some random permutations. Okay, so these edges, and then you can define a Markov chain due to this graph. Okay, well, once you normalize it appropriately. And then you can show that this guy has a small second eigenvalue. Okay. So recall that its top eigenvalue is 1, despite normalization. So really, this is a Markov chain. And if you apply this many times, because the second eigenvalue is small, it's going to converge to the uniform distribution. Okay. It's a top eigenvector. Okay. So well, why am I telling you this? This is the classical case, doesn't seem very relevant. However, this very similar phenomena happens in a quantum case. You have to have some imagination here. So Hastings shows that if you replace this permutation by random unitaries, okay, independent random unitaries, then you get a quantum version of this. Okay. In particular, it's written in the sense of a spectral mixing. Okay. So it has a small eigenvalue, a second eigenvalue. Well, so now you have a big Hilbert space. It's not like discrete, it's not like a graph. It's harder to imagine what's happening. But nevertheless, well, we can have a simple picture that all it's doing is that if you, whenever you put some state, it's going to spit out very orthogonal vectors. Okay? So if you repeat this process a few more times, it's going to quickly populate the entire Hilbert space. And that's how mixing happens. And you can also understand it entirely in terms of the spectral properties. Okay. For us, we're going to write down a slightly more technical condition. It's in terms of concentration. So we're going to subtract this map from its expectation. Okay, we're going to take the difference in this form. And then we're going to take the spectral norm. Okay. So right now, this looks very technical. This is just another way to think about the second eigenvalue, I guess with absolute value, perhaps. But this will turns out very important in our proofs. Okay. Okay, so let's now apply all these ideas in our case. So recall we have this semi-classical object that's like a random walk. And then we want to know how this local coherence get lost and how it mixes to the thermal state, the Gibbs state. Well, so what are our assumptions? We have some random matrix assumption from ETH. We say that these guys are random matrices. They're independent random matrices. Okay. And then due to this expander property, you can say that this map is going to be very close in appropriate distance to the expected map. Okay. Well, so what's happening here? Well, so now I introduce some artificial object, the expectation. So what is it? Let's look at it. It turns out it is closely related to the Davis generator I've been telling you in the beginning. Well, so what's happening here? So what's the Davis generator is actually a classical random walk. So in other words, this expected map is very simple. It's a classical random walk, and you can take out your Markov-Chain textbook, and then I guess do some conductance estimates on bounding the mixing rate of this classical walk. Okay. So from here, the proof is very simple because you just reduce a classical problem and then you can do all the calculation. Okay. So indeed, this is what all the parameters comes in, including the bath transition rates, the bath temperature, all these things. It all just comes in this last step. Okay, so to reiterate, you start with this semi-classical object. Okay, it's because I say there's energy time uncertainty principle, you can resolve the nearest eigenstates, and it becomes very nasty to analyze because it's like some very quantum process. However, if you assume ETH, then you reduce your problem to this classical object that you know how to analyze. Okay. Remarkably, I have been telling you that this Davis generator is unphysical. You can't produce it out of a very short runtime. It's restricted by an energy time uncertainty principle. But the story comes back to it, and but now it shows up as a proof technique. It's an artifact that shows up in your proof. It's not physical, but somehow it governs the thermalization rate of the process of interest. Okay. So this is a proof. Any questions? All right, so if no questions, let me move on. So this is the end of our near the end of the talk. Let me quickly summarize. Today we have been talking about thermalization in open system. So this is the setting we consider. We have our system and then we couple it weakly to our bath. There are some additional technical assumptions that's definitely flexible. We can change it in some way. It's not terribly important that we write it down for concreteness. And then we talk about this semi-classical object as a toy model for what's happening in above. So largely, we have only talked about the rounded Hamiltonian. It's like a much simpler version. You could consider the unrounded case, it becomes slightly more technical. But we think the picture is very much the same. And in order to show its convergence, we assume ETH. Okay? We'll assume that different operators in the energy basis in this tiny band behaves like independent random matrices. Okay? And then, because of properties of random matrices, they're very good scramblers. They're like Connick expanders. You can compare this process of interest to a much nicer classical process. Okay, and then here you do all the calculation. So that's all I've been telling you. And for future work, let me just briefly comment. Definitely a very natural generalization or direction is to ask if we can actually prove ETH. Because ETH is kind of like this conjecture. It's quite flexible. It's not very clear which one is the true one. I think it's possible to do it for some of these nicer matrix ensembles. And this polystring is like a sparsification of it. This might be doable. And next, I think, indeed, as people mentioned, can we remove the Markovian assumption? Or say maybe by changing the assumptions of ETH, maybe you make the whole system ETH, or you make other assumptions. I think those are all possible. But as I mentioned, this will likely change the proof strategy. Because right now you have some map and you're iterating the map. You're kind of controlling the spectral properties. So if it's not Markovian, then you lose all of that. Okay? So you have to come up with different techniques. I think it's possible. Okay? And further, perhaps more on the algorithmic side, you can ask if we can imitate this entire process without the bath. That will be quite interesting. But it might have slightly different consideration because now you may be worried about the resource cost and how much, how expensive is it to implement all these things. Okay, so that's all I have you for today. Thanks a lot for all the questions. It's really fun. Yeah, and I will take any questions you have. Thank you.
Yeah, thank you very much. So so we still have a question time for 5 minutes. So is there any question?
Yeah, sorry, I have a question. Can you pronounce? Can you hear me?
Yeah.
So my question regarding the dissipator generator of your motion. You said like every jump operator is considered as a random matrix, right?
Right.
But what about the coupling braids? Can you consider them as a random variables as well? Like, didn't give like some
the what?
Like the gammas, like gamma W.
Oh no, gamma is just some function of the path. It doesn't.
Like
so it's some particular function. It doesn't depend on ETH.
And can you make it random? Like I've seen some works regarding like random Liouvilleans where you also consider random coupling rates. Like, would that be
I guess
hard? Like,
I think it depends on where you put the randomness. If you change gamma, I'm not sure. Like if you introduce other source of randomness, maybe.
Yeah. Because somehow that gamma is related with it's derived from a correlation function, right? From the system.
Right. That's right. Yeah. I think it's going to be pretty smooth. I mean, maybe you can change it. I mean, it's tunable. It's tunable.
Okay.
I'm not sure if it will help on the mixing part.
Okay. Another question, like your jump operators are Hermitian? Like,
Right.
Okay, so your system thermalizes the infinite temperature, like, and the long time limit.
That's right.
Right? Can you consider like non-Hermitian jump operators as well?
Probably. It might make things slightly more complicated because
maybe you have like non-steady state, like long time limit behavior. That might be interesting to consider. I'm not sure.
Yeah, I haven't considered very carefully when things are non-Hermitian.
Okay.
Yeah, I'm not sure. Yeah.
Thanks.
There is one question from the Professor Munyandi. So maybe I read it in chat. Can information back from the environment be used as a resource for this formalism? This is a question from the Professor Munyandi.
So right now we try to avoid that. I think we just want to make sure it's Markovian, so make things simple, make our library simple. We don't consider the fact that this back reaction from the bath. And yeah, so I don't know what happens there. Maybe it will be helpful, maybe it will not. I don't know. Yeah, but right now it's all Markovian, so it's like this more simplest, like the vanilla version of thermalization.
Professor Munyan, this is okay, or you have some extra comment, or? Okay, so maybe. Oh, is there any other question? We still have maybe 1 or 2 questions. The time to the.
So then, can I ask a question?
Yeah. Please.
So what is the meaning of delta RMT?
Yeah, it's
the physical meaning of with this.
Right. So right now, I think that's quite mysterious. I think I asked some people who really try to understand all the scales in random matrix in ETH. So based on what they tell me, it is the time scale where everything ends. Because it's maybe kind of vague. So I think what they tell me is that you might expect this mixing behavior to even occur even in a bigger band. So right now maybe there's some improvement. That physical argument can lead to improvement. Yeah, but right now I only know that this somehow it's like the time scale where everything ends. Yeah.
I see. So that sets some time scale in the system. I see. Okay,
yeah, it's like the latest physical time scale in the system. Yeah. I think they say that this might have like the thermalization should occur faster. But right now I don't know what assumptions to use. Yeah.
I see. Yeah.
So definitely like all these could happen much faster at a much faster time. But you have to choose a good assumption for that. Yes.
I see. Yeah. Thank you.
Okay, so is there other question? It's actually it's almost a time. If there. Okay, so if there's no question, then so let's thanks to the speaker. So thank you very much. Very interesting talk.